Hello, I'd like to go over the first quiz, the practice quiz we took with you, so you all know how to get the correct answers and solve the problems. The first question has to do with determining the rate law based on some information that you're given. You're given initial rates and initial concentrations of the reactants. This means it's a method of initial rates problem. In the method of initial rates, we can look at the ratio of the rates for any two of the experiments. We can pick the ratio of the rates for the first experiment and the second experiment. We can see that the concentration of B stays the same, but A changes. If we look at the ratio of the rates and the ratio of the concentrations of A, we can determine what the reaction order of the reactant A is. We can do that by setting up that ratio. The rate of experiment 2 divided by the rate of experiment 1. We know that the rate of experiment 2 is always going to be equal to the rate constant times the concentration of A to some power times the concentration of B to some power. We can do the same thing for rate 1, where we have K times A to some power times B to some power. We can add in the information to this equation, so it'll look like this, where I've simply filled in the ratio of the rates on the left-hand side of the equation and the ratio of the rate law portion of with the concentrations involved in the right-hand side of the equation. I can simplify both sides of the equation, so we end up with 9.11 is equal to, where the rate constants reduce to 1 and cancel out, the concentration of B in experiment 2 and experiment 1 are the same to some unknown power. That reduces to 1 and cancels out. So we end up with the 9.11 equals 0.0510 molar to the M divided by 0.0170 molar also to the M. Now by rule of logs, the 9.11 is equal to the 0.0510 divided by 0.0170 all to the M. And this tells us effectively that the 9.11 is equal to 3 to the M, where M equals 2. We can repeat this now with a set of experiments where B changes in order to determine the effect of the concentration of B on the initial rate of the reaction. We can set the same kind of thing up, picking any other two experiments. In this case, I'll use experiment 3 compared to experiment 1. I can set that up just like I did before. So you can see I've got the relationship between the rate of experiment 3 to the rate of experiment 1, and I've used the concentrations from the above table, including the exponent for reactant A, which I determined in the first step of the problem. Notice that we don't need the concentration of A to be the same in both cases, because we know the exponent. We can just do the math now that we have the exponent and figure things out from there. We've got the ratio of the rates, which is equal to 212.6. And that's going to be equal to the simplification of the A squared terms, which works out to be 13.3, times the simplification of the B terms, which works out to be 4 to the n. 4 to the n is then equal to the 212.6 divided by 13.3, which works out to be 16.0. So we can see by inspection that n equals 2. We now know the rate law for the reaction, where the rate is equal to the rate constant times A squared times B squared. In order to calculate the rate constant, we can simply add the concentrations and the rate for any of one of the experiments to determine what K is by doing some simple algebra. It's actually a good thing to check. You could check 2 of the different experiments, maybe experiment 1 and experiment 2, compare the value of the rate constant you get in both cases. The rate constant should be about the same, maybe not exactly the same, but about the same. So I'll show you what that calculation looks like. So I've got the concentrations plugged into the rate law. I rearranged the algebra right below. And notice I carried through all the units for the rate in terms of molarity per second, and then the molarity squared and molarity squared for each of the reactant concentrations. If we look at what happens to those units, we see that the per second stays the same in the denominator for the rate, but 1 molarity is going to cancel out with one of the molarities, numerator and denominator. This gives us a value of 62,400. And the units would be molarity to the -3, seconds to the -1. Notice that the rate law is always written with the rate and a rate constant in sort of generic terms. The exponents, of course, are there, but since the rate constant changes with temperature, the rate constant's never used as a new number inside the rate law itself. Moving on to question 2. Question 2 asks about the decomposition of aspirin, and we're told that it has a particular rate constant. In this case, the rate constant has units of molarity to the -1, seconds to the -1. And that tells us exactly what order the reaction is. It tells us it's second order. So we need to use the second order integrated rate law. So here's the second order integrated rate law. We can then add in the initial concentration and the rate law and the time and figure out the new molarity at a certain time period. Here is the second order rate law with the initial concentration and the rate constant and the time multiplied by each other. We can then solve that algebraically to end up with this. 1 over the aspirin concentration at our time of 24 hours is going to be equal to 1296 for the KT term with units of molarity to the -1. As we can see, the units here, seconds and per second, reduced to 1 and cancel out, leaving us with molarity to the -1 as the unit. We have to add to that the 2.5 molarity to the -1 term from the 1 over aspirin sub 0. And we end up with a new aspirin concentration after we do the arithmetic of 0.000770, and we would end up with units of molar. The intermediate step, of course, is that 1 over the aspirin concentration is equal to 1298.5 with molarity to the -1 as the unit. Then we take the inverse of that number to get the final answer for the new aspirin concentration. Question 3 asks us about the rate of disappearance of one substance given the rate of appearance of another substance in a chemical equation. If you remember, we can use stoichiometry to figure out a problem like this. We know that the initial rate of appearance of sulfate is 6.00 times 10 to the -6 molarity per second, and that's molarity of sulfate, SO4 2-. We know that in terms of the mole-to-mole ratio, there are 2 moles of sulfate for every 3 moles of iodide. And so we would end up with moles of sulfate reducing to 1 and canceling out. We would end up with 9.00 times 10 to the -6 molarity per second for the rate of disappearance of iodide. Next question has to do with caffeine in the blood, which has a half-life of about 5 hours. I looked it up. We're told it decays by a first-order mechanism, so we're going to need the first-order integrated rate law. So here's the first-order integrated rate law for the disappearance of caffeine. We can add in the concentration and time and rate constant information. And we'd end up with this expression. Notice that we don't know the rate constant at this point, but we do know that the caffeine in blood has a half-life of 5 hours, and it's a first-order process. So we know that the half-life in a first-order process has an equivalence of 0.693 divided by the rate constant, or we can calculate the rate constant by taking 0.693, dividing it by the half-life of 5 hours. So we know that K is going to have a value of 0.139 hours to the minus 1. Don't forget the units. We can now add in the value of the rate constant to this problem, and we can simplify this to show that the natural log of the caffeine at some time divided by the 5.00 times 10 to the minus 6 is equal to the negative 0.139 hours to the minus 1 times 17.5 hours. Algebraically, it works out to this last expression here. We can solve for the caffeine concentration at some time by exponentiating both sides as the power of base e. In order to solve the e to the negative 2.433, you'll need to use the second function of the natural log on your calculator. And then we can just use arithmetic to solve for the concentration of caffeine at some time, which will be equal to 4.39 times 10 to the minus 7 molar. Notice that this number is less than what we started with, the 5.00 times 10 to the minus 6 molar, which leads us to believe that we might have solved the problem correctly, seeing as how the reactant concentration should go down over time. We're almost done. 2 more questions. When's the rate constant constant? For any reaction at a single temperature. Last question. The reaction A goes to 2B, A plus 2B goes to products, has a rate law where A is third order and B is first order. We can write that rate law. Rate equals K A to the third times B to the 1. If we have a situation where A is doubled, and B is doubled, regardless of the value of the rate constant, if we have 2 to the third power, that's going to be 2 times 2 times 2, or 8. We have one more 2 to multiply by, so the entire rate of the reaction would go up by a factor of 16 times what it was before. Hopefully you included all your units and solved all the problems correctly on your quiz. If you have any more questions, come and see me.